Hi everyone, I'm Emily, and in this video I will explore some of my understanding on this unsolved mystery Riemann hypothesis. In this video, we will discuss prime numbers, a special subset of natural numbers, and the Riemann-Zelda function, their connection, and the Riemann hypothesis, an intriguing mathematical puzzle. Let us start with prime number. It is a special set of number that can only fully divided by 1 and itself. Prime number are very important since every possible integer greater than 1 can be represented as a product of prime numbers. The prime numbers are the cornerstone of the natural number system. But the statement of Euclid's contradiction that there exists infinitely many prime numbers in the set of natural numbers. Therefore, finding its distribution is fairly important for future research. Prime numbers appear to be scattered among natural numbers without an obvious pattern, posing a challenging question for mathematicians. How do we understand the distribution pattern of prime numbers? This question has been a constant companion of the development of mathematics, attracting the exploration of countless mathematicians. Complex numbers are a combination of real and imaginary numbers, where the imaginary unit is typically denoted as I, defined as square root of -1. Complex number can be represented as point on the complex plane, with the real axis representing the real part, and the imaginary axis representing the imaginary part. And in this PowerPoint, we can say that A is representing the real number, and the B with the I is representing the imaginary number. The Riemann hypothesis is a famous and solved problem in mathematics, first proposed by the 19th century German mathematician Bernhard Riemann. The purpose of the Riemann hypothesis is to gain a deeper understanding of the distribution pattern of prime numbers, despite substantial evidence in support of it. The hypothesis has not been rigorously proved to date and remains a major challenge in the field of mathematics. In 1859, Riemann was appointed as a corresponding member of the Berlin Academy of Science. As a gesture of introduction, Riemann submitted his only paper on number theory. The paper was titled "On the Number of Prime Less Than a Given Number." Indeed, this paper, despite its brevity at just 9 pages, remains one of the most significant contributions to the field of prime number research. In this article, Riemann provides his hypothesis of the exact expression for the prime counting function. This equation can be seen as 2 parts, Gx and error term. Gx is the main part of equation and will be explored in following slides. This is the error term where it gives a correction to the prime number given out. The top part is known as Mobius function. This equation states that when the equation equals to 1, the product of an even number of distinct prime numbers, when equals to -1, n is a prime, or the product of an odd number of distinct prime numbers. When equation equals to 0, n contains a square factor. The entire expression means that after adjusting for the correction term, Riemann's prime counting function, which is Gx, is exactly equals to pi x. Before we explain what is Gx, we need to know what is Riemann's zeta function and what is non-trivial zero. Here, s is a complex number. When s is a real number, this function can be expressed as a series. However, the most intriguing aspect is when x is a complex number. The Riemann zeta function exhibits complex properties. The domain of the Riemann zeta function is a complex plane, which means S can take any complex value. This makes it a multivariable function with complexity beyond regular and real functions. The Riemann zeta function takes interesting value at certain special points. For example, when S is equal to 2, it yields the solution to the famous Bézier problem, where zeta S equals to pi squared over 6. Trivial zero is when S is equal to negative 2n, where it is a real number, which is easier to calculate than non-trivial zero. Non-trivial zero is when S is equal to a plus bi, where it is a complex number and still was not found out all of them in our day. Riemann hypothesis focused on the non-trivial zero of the Riemann zeta function, where zeta x equals 0 even when S is not a negative even integer. The hypothesis suggests that these zeros all lies on a special straight line in the complex plane, known as critical line. The resolution of the Riemann hypothesis is closely tied to understanding the properties of Riemann's zeta function. Let's get back to Gx. It can be separated into 4 parts. Riemann-Liouville function, sum of p of Lie xp, where p is a non-trivial zero, a constant, and the integrate equation, where for that equation, when x is greater, the result of the equation will become smaller. When more non-trivial zero involved in the calculation, Gx is more close to pi x. Based on the analysis above, if we could know all the non-trivial zero p of the zeta function, then we could obtain the exact value of pi x. However, finding the non-trivial zeros p appeared to be as challenging as determining the precise distribution of prime numbers. What can be done? If we know the range of p's as well, where real p represents the real part of p. If real p is between 0 and 1, then the prime number theorem holds, which has already been proven. If real p is equal to half, this is actually another way of describing the Riemann hypothesis. If the Riemann hypothesis is proven to be true, then we can prove that this equation is equal to pi x, which tells us the error between the prime counting function pi x and the logarithmic integer function Lie x. Proving the Riemann hypothesis will be a significant step forward in understanding prime number distribution. However, this is just the beginning, and we're still far from fully understanding the true distribution of prime number. At the end, let us state Riemann hypothesis again. The Riemann hypothesis focuses on the distribution of non-trivial zeros of the Riemann zeta function. Especially, the hypothesis states all non-trivial zero lies on the special line in the complex plane called the critical line. The mathematical representation of this special line is S equals to half plus bi. Here, x is a complex number, and the b is a real number. This line in the complex plane is perpendicular to the real x and is located at the real part of half. If the Riemann hypothesis is true, it will provide a crucial tool for number theory and help solve problems related to prime number distribution. Until today, we have had over 1 billion non-trivial zeros were calculated out, and all of them are lies on the critical line. After 1/2 century, we still can't prove Riemann hypothesis or deny it. Overall, thank you for your watching today. And if you have any question, leave in the comments.